All right, so let's start. This is where we left last time. Right, so we talk about supremum property. Right. So first we define the terminologies. What is supremum and what is infimum? Right, and then basically before that we define what is an upper bound and what is a lower bound, and then we see that what do we mean by bounded above and what do we mean by bounded below. Right. So if the set has upper bound, then it is bounded above, and if a set has a lower bound, then it is called bounded below. And then the least upper bound is called the supremum, and the greatest lower bound is called the infimum. Right? So we see all these things last time, and then we write down the axiom. Right? So axiom is a statement which we assume without proof. So we assume that, or we take the axiom that every non-empty subset of real numbers that is bounded above will have a supremum. Right? So that is the axiom we studied last time. Right? So now because this axiom is for supremum, right, we shall develop similar kind of results for infimum as well. Right, so we will write that as a theorem, because once we have an axiom, we can use that axiom to prove all the other results. So let me write down as a theorem. We call it infimum property. Okay, so every non-empty subset of real numbers that is bounded below has an infimum. And so this is the infimum property. We can show this, or we can prove this result by using the completeness axiom, which is also known as supremum property. Right? So let us try to prove this. And so first we will take an arbitrary non-empty subset of real numbers. Right? So we have to set the hypothesis. The hypothesis says every non-empty subset of real number which is bounded below. So let's take an arbitrary non-empty subset, right, of real numbers, right, and let's say that is bounded below. And BDD, which means bounded, right? So is bounded below, right? So if S is a subset of real numbers and it is non-empty and it is bounded below, so definitely it will have a lower bound, right? So okay, so sorry, because S is bounded below, there exists a lower bound L such that all the elements in the set X is greater or equal to that lower bound, right? So what we do is we multiply this inequality by -1. So when you multiply the inequality by -1, you know, we already studied that, right? Under the second axiom, order properties, when you multiply by minus, the inequality switches the side. So the inequality reverses. And so then x greater or equal to L means minus x less or equal to L. And that is true for all x in S. So, but now we have some new terms minus x, right? You start with x, but now you have minus x. So let us define a set that contains all such minus x. So let us take the set of all minus x, right, such that x belongs to S, right? So this set is a set of all minus x. So clearly you can see that, right? Because S is non-empty, T will be non-empty. Because S is a subset of real numbers, T will be a subset of real numbers, right? And because of this results, for all the x in S, that means for all minus x in T, minus x is less or equal to minus L. Right? So T is clearly a non-empty subset of real numbers that is bounded above. So you can apply the supremum property, right? So by the completeness axiom, you can say that T has a supremum, right? So you can name the supremum, right? You can name the supremum now. Right, so because T has a supremum, let us name the supremum as U, right? So this is the supremum. Now, what do we mean by supremum? That we all know, right? Then okay, so all the elements in T are of the form minus x, right? So let me name some terminology, right? So then T is less or equal to U for all small t belongs to capital T, right? So because U is the supremum, it is an upper bound. So that means every T will be less or equal to U, right? But you know, but T is actually a minus X because that is how you define the set, right? So if you combine both of them, right? So because U is the supremum of T, small t is less or equal to U for all T belongs to T. But you know, every T in T is of the form minus X for some X in S. So that means minus X is less or equal to U for all X in S, right? So that gives X greater or equal to minus U of S. So clearly, right, by the last statement, we can clearly say that because X is greater or equal to minus U for all X in S, we can say that minus U is a lower bound of S, right? So now, because minus U is a lower bound of X, and you know what is U? U is the supremum of minus T, and minus T is a set of all minus X for all X belongs to S. So basically, this minus U should be the infimum of the set S, right? Because you remember, we start with a non-empty set S and we try to find the infimum of that, right? So in this case, we from that S we go to another set, right, which has a supremum, and then we take the minus of the supremum, and we are trying to show that that is the infimum of the original set, right? So we come all the way to minus U is the lower bound. Now we have to say that this is the greatest lower bound, right? Right, so let U dash be the greatest lower bound of S, right? So X is greater or equal to U dash for all X in S. So that means minus X is less or equal to minus U dash for all X in S. So that means minus U dash, it's an upper bound of T. Right? We assume that there is another lower bound, another lower bound, U dash, right, for the set S. Right? If U dash is another lower bound, then clearly every element in the set should be greater than the lower bound. So X is greater or equal to U dash. But we know that we work on the minus X set. So you multiply by minus again. So you get minus X is less or equal to minus U dash for all X in S. Same argument like earlier, right? So this has a supremum, this will have an upper bound, right? So U dash is an upper bound of T, right? But we already defined that u is the supremum of T, and u dash minus u dash is another upper bound of T, right? So you all clearly know by the definition of supremum, it should be the least upper bound, right? So clearly, u is the supremum, u minus u dash is an upper bound, so u will be less or equal to minus u dash, right? So, but we start with u dash, so you want to get plus u dash, so you can multiply by minus. So that means minus u is greater or equal to u dash, right? So here you have minus u dash is a lower bound, right? And u dash is any other lower bound, and you get minus u dash is greater or equal to u dash, right? So any other lower bound is smaller than minus u dash. So that means minus u dash should be the infimum. Right. So then hence minus u is the infimum of S, right? Because for any other lower bound, right, that lower bound is smaller than minus u dash. So clearly minus u dash should be the greatest lower bound for the set S. So that means minus u should be the infimum of the whole set. So that is how we prove the infimum property by using the completeness axiom or the supremum property. So this is one of the key proofs of writing the relationship between two properties, right? Infimum property and supremum property. Right? You can always prove the other way around as well. Right? So I will give that as a homework, right? You can try your own. Right, so as a homework, what you can do is you can assume that infimum property is your axiom, right? And then by using the infimum property, try to prove that the supremum property is true, right? So here what you are doing is you are going to assume that every non-empty set subset of real numbers that is bounded below has an infimum. And then by using that, you are going to prove that every non-empty subset of real numbers that is bounded above will have a supremum. Right? So this is kind of opposite way of going in this proof. So that gives you that you can always go from one property to the other, right? From supremum to infimum or infimum to supremum. Right? So this is a homework. Right. So now we will go to one of the examples, right? Where we use the supremum, right? You remember when we are talking about boundedness at the beginning of this section, right? I mentioned you as an example that set of natural numbers is not bounded above, right? So I just mentioned as an example that set of natural numbers is not bounded above, right? Intuitively, you can see that, right? So you cannot say this is the bound because you will always have one more number than that. Say, for example, if you say 1 million is the bound for natural numbers, but you know 1 million one is there, right? So if you say 100,000 million is the upper bound, then 100,000 million one is a member of natural number. So intuitively you can see that you cannot bound the natural numbers, but theoretically, mathematically, you have to prove them, right? So to prove it, it is true for all. And last time when I write the example, I started the proof, but then I erased it because I told you that we have to come back it later, right? So now we will do the exercise or as a proposition and show you that natural numbers, set of natural numbers is not bounded above, right? Because we are going to use supremum, the notion of supremum to prove that result. That is why I skip the proof there and I'm doing it here. And so I will write it as an exercise. And so show that the set of natural numbers n is not bounded above. Right. So what we are going to do is we are going to prove this by the method of contradiction. So assume that right. So let us assume that n is bounded above, natural number set is bounded above, right? We want to show that it is not bounded above. So for contradiction, let us assume that it is a bounded above set. So by completeness axiom, right? So by completeness axiom, so clearly n will have a supremum, right? So because n is bounded above, we assume that n is bounded above, right? We can say that n has a supremum. So if n has a supremum, right? So let's say let us say supremum of n is equal to u, right? So that means